Okay, so today we'll talk about interpreting parameters in longitudinal models, and towards the end we may talk about missing data. Why is that of relevance to longitudinal modeling? Well, a lot of the simple studies and experiments you do where you just get one measurement per subject, dropout isn't really an issue. But when you have longitudinal studies where you're following people over time, there's a chance that a lot of people, for one reason or another, they'll drop out. They may just get tired of participating, or there may be various reasons, but just fairly inevitably, you're going to have dropout. In large longitudinal studies or experiments, it's just going to happen. So the question is, how do we deal with subjects that, for one reason or another, we don't get the full span of measurements on those subjects? So there's a lot of methods that have been developed to account for dropouts, because the real question is, are the people that are dropping out because of, maybe they're sicker, or maybe they're better, or whatever reason? It could be tied to the outcome. And so that's going to impact your estimates, right? Your progression estimates. And so we need methods to account for that. So we'll probably start talking about that towards the end of today. Initially, I want to talk about interpreting parameters. So that's the first set of slides that we're going to go through. And am I sharing my slides? Okay, thanks. So some pretty interesting stuff here. I think I always say that, but this was developed over several years, that I've been teaching this class, and some pretty interesting, maybe slightly unusual results here, but very informative. We start talking about time varying age versus baseline age in longitudinal models, and then we'll talk about how to separate within and between subject effects for time varying covariates, and mainly those two, and then we'll jump to population average versus subject specific effects, which we brought up a little bit when we talked about generalized linear mixed models. So we'll go through that more thoroughly today. Those are really the three main things we're going to talk about. I'm going to skip over a little bit of the stuff that's in the slides, because some of it is, how you write custom tests for, especially for continuous time in the model, or a continuous predictor. And we did that pretty thoroughly. So I'm gonna jump over those slides when we get to them. But if you have any questions, certainly you can reach out to me. So the question is, like, if you have a study or an experiment, and this may, be something that you're directly facing with your project, where you have a time variable, so you take measurements maybe at baseline, and then let's say 2 months, 4 months, 6 months, or something like that. So you already have one time variable in the model, but you also have age that you want to adjust for in your model. So the question is, do you use baseline age? Since we already have a time variable, should we use baseline age, or do you actually put their real age at each visit in the model? And this is something that I really wrestled with for quite a while. And then I actually just said, I'm going to figure this out. I'm going to figure out the relationship between these and the outcome. And so that's what we're going to walk through now, is mathematically, like, showing what you get when you put in just baseline age or real age, and then you compare the two. So it's a little bit like what we did in the homework, where I asked you to compare the baseline as covariate model with the hybrid model to show the relationship, right, between the two. So this is something you kind of already have an idea probably how to do it. Now we're talking about the relationship between baseline age so like a fixed age in our longitudinal model, or using the actual age at each visit. So in a nutshell, this is the relationship. So, if you want to think of a data set, maybe think about, taking subjects' blood pressures over time. Let's say we have a number of time points equally spaced, and we're going to include time in our model, to indicate, when we started, and then the gaps in between the repeated measures that we're taking, essentially. And we can use an AR1 structure or something like that to account for the repeated measures on subjects. So the key thing here, and I believe this will work, I'm confident today. Why it didn't work, I have no idea. Like after I got out of Word and I brought up another document after the class, I didn't do anything special, it just started working. So it was just messing with me on Monday, and now it seems like it's working. So I'll be able to use my pen. So we have this expression here. So real age is the baseline age plus time, and that's if we have time 0, and then I'll just say T1, T2, etc. So the key is that the first time point is our baseline, right? And that's 0. And then this could be, it could be let's say 1 week, 2 weeks, something like that. So this expression we have for the actual age, we can break it down into the age at baseline plus our time variable, right? So that I think that makes sense, right? So we can take that, our model, and plug in for real age. I'm going to plug in based on this relationship that I have, baseline age plus time. Then I'll pull the beta 1 through, and we have 2 time terms in the model, right? So I can combine the beta 1 and beta 2 together and end up with this model. So this shows you the relationship between the model that uses real age, the actual age at each visit, and baseline age. And what's kind of unusual here is that if you fit, let's say we use real age and we use time as predictors in a model, we fit that model, and you compare it to the model where you use baseline age, what's the parameter that's going to change here? What's being suggested by what I did here with these derivations? What is the parameter that's actually changing? For which predictor? See if you're with me here.
Should B2 grow because it's taking some of the effect that real age had earlier?
Yeah. So you'll see that we have the coefficient for time is a combination of beta 1 and beta 2. So this parameter that we're estimating is actually combining from this original model, our beta 1 and beta 2, so it's going to be larger, right? It's combining those effects. Whereas even though this predictor here in the middle is different, the coefficient's the same. And you can try this, put in your own data, and I have some as well I can show you, but even though we're changing that middle variable, the slope is actually going to be the same. The one that changes is the coefficient for time. And so what is this telling us? It's saying that if you want to estimate effects that don't involve age, then you want to actually put in the real age at each visit. And then your time variable, your coefficient for that is not going to involve age. But if you put in baseline age, then the coefficient for time is actually going to be a combined effect of time plus age. So doesn't that seem a little strange? That, you know, when I first saw this, I was like, that's weird, but I fit data to it, and sure enough, you know, it reflected what I've shown here in these equations. So in a nutshell, if you want to, you know, let's say time would represent a progression effect. So like if we're studying a certain disease or something, time is going to represent the effect for time would be the progression of the disease. And if you want to eliminate aging effects, then you need to put in real age and not baseline age. Okay. Now, like for another way to think about this, you know, are you guys familiar with percent of predicted FEV1 or FEV1? Are you familiar with FEV1? It's a lung function measure, right? So the higher the value, the stronger the lung, essentially. And percent of predicted is basically adjusting relative to what you'd expect for somebody of the same age, race, height, and sex. So you can get a percent of predicted. So like, for example, 90% FEV1 would say that person's FEV1 is 90% of what you'd expect for somebody of that same age, height, sex, and race. And so if we want to estimate effects for FEV1, commonly we would adjust for whatever age they have at a certain visit, right? Certain height, certain race and sex for that person. And so that's what we'd be doing. We'd be using the age specific value at each visit. And by doing that, then if we see changes over time, then it's more likely due to the disease itself and not due to the aging process. Okay. But in general, then, if you just have predictors that you're adding in and you want to understand, you know, patterns of disease progression, then you'd put in their actual age as a predictor, not just baseline age. Somebody last year brought up the question. They said, well, isn't that going to lead to collinearity? If you have time, plus you have age, that seems like it's very related to that. And I have a supplement I can add that shows that that's typically not going to be an issue at all. So are there any questions on this?
Yes, a really quick one. When you use the real age and the time, does that mean you introduce a confounder in the situation because your time affects both your age and your outcome? So I would think it's more like a confounding other than a collinearity. Right? It's like a confounder for time, right?
It's not really the thing is, we can, if this is true, okay, if we can express real age as baseline age plus time, we know exactly what we're estimating. And we know the relationship between the model that has baseline age and real age. And in fact, you can, even if you fit the model with baseline age, right, with an estimate statement, you'd be able to derive out beta 2, the estimate for beta 2, even though you fit that model. It's kind of like the hybrid versus the baseline is covariate. You understand the relationship between the two. So to answer your question, you know, confounding, I don't really look at it as confounding. You know, like if you consider the change in the beta 2 estimate from the first to the last model, beta 2 versus beta 2 new, and you see that it changes, you know, you could maybe argue technically that there's confounding, but we understand perfectly what we're estimating, and we understand how to tease out the effect for time, even if we fit this beta 2, even if we fit this last model. So in it, you know, essentially, I don't view it as confounding.
But what if we introduce like more things like a random slope for time and age? Then in this way, we would not exactly know what exactly is the relation between time and the real age, right?
I still don't think it's going to cause a problem, because the baseline, like if you have a random slope for time, I'll think about that next question that you just asked me. But I still don't think it's going to cause any problems in us being able to estimate the slopes of interest in our model. But let me think, Randy, let me think about that a little bit more and see if I have any follow-up thoughts. I'll mention
I think even if you think of it as a confounder, usually you want to include all your confounders. So even if you think of time as a confounder, it would mean that you would want both in the model.
That's a good point. Yeah, usually for confounders, you put everything in that you want to adjust for, right? That's a good point, Carrie.
And I think in this case, it's just like we adjust the real age from the model 1 just like directly by changing the covariate of time, right? It's just like we already know what's the effect of the compounder over there. And then we put the compounder's effect on the beta 2, right? For example,
Yeah.
if we have some other variables time related, and we will definitely include that into the model.
Yeah.
I think it's like similar to the real age, right?
Yeah. Yeah, some good thoughts. Anybody else? I'm going to turn up my volume here so here it goes a little better. Any other thoughts or questions on this?
So when you've done this in real data, let's say the visits are every 3 months or something, so maybe 4 visits, they don't actually change their age. Are you creating like a continuous age where you actually add like 60 years old plus 3 months? Or are you just saying 60, 60, 60, 60? Does that make sense?
I go to decimals. Yeah. I mean, if it's,
Okay.
you know, so you can say, you know, 60, 60.1, 60.2 or something like that, you know, and actually get the specific amount. Because again, if you round it, then you're kind of going back to that initial model or the, you know, the baseline age model. And it's possible, like if you're between subject differences in ages is much bigger than the time frame that you're looking at, then it may not make much difference to do this, right? But typically, you know, we're pretty quantitative people, right? I'm assuming. So we keep things to decimal points that we need to. So again, maybe the impact won't be great, maybe it will, but typically we do it, you know, just to be more exact in our analyses.
So Matt,
yeah.
If for example now from this model we want to estimate change for a given unit of age, for example, how would we be able to do that from this? Or that's not possible from this model?
Yeah, I mean, so essentially you can do that, Benjamin, you can do that, but the effects, and we're going to talk about in the next slides, talk about this a little bit more later, but the effects for beta 1 are actually going to be based on differences between subjects. So it's a between subject effect, whereas the time effect is a within subject effect. Okay, so we can do it, but we have to remember that, you know, that effect that we're estimating for age is based on differences between subjects, right? And it makes sense because if we're following everybody the same amount of time, you know, time 0, time 1, time 2, time 3, then really to get the impact of age, we have to base that on the differences between ages of the subjects. You know, and I will illustrate that even more in the slides coming up. So I think the points that I have here really are what we've talked about. Most of the studies that I've done that involve age and a time variable, I put in real age as well as a time variable in the model. And so I've done that. One I've mentioned is the natural history of beryllium. So I presented that data before. COPD gene study is a big one, and I do the same thing for that. So some of you that may be an issue for the data that you have in your project. For some of you, it may not. So I imagine for at least some that it will be something you have to think about. So a very related topic is separating, if we have a time varying covariate in a model, we may want to separate out the within and between subject effects. And there's a very clever way to do that was published. I mean, maybe the idea has been around for a long time, but somebody published about this, I think 15 or 20 years ago. And so we're dealing with, you know, in longitudinal models, we have multiple subjects typically, right? Unless we have that one process thing that we've looked at before. But most longitudinal data involve multiple subjects. So we're going to get, you know, data on different subjects, and then we're also following subjects over time. So our covariate, and in this example that I'm talking about, let's say it's air pollution, and we're measuring subject-specific levels of air pollution that they're exposed to. And we can do that if they, you know, they wear a personal monitor. You know, they may live in a place where they're exposed to more air pollution or maybe less. You know, maybe they're in a home that's where there's, you know, where they have better cleaning, you know, HVAC or whatever. So they're exposed to less air pollution, and some may be exposed to more. So it depends on where they live and their housing and stuff like that. So our predictor in that case, so let's say, for example, air pollution exposure. It depends on the subject and also the day. And so this indicates that there's going to be a combination of both between subject differences and within subject changes over time that's going to contribute to the coefficient in front of that predictor. So what if we want to separate out the between subject effects from the within subject effects? What can we do? Well, there's a clever way to do that, which this paper showed, where we take that time varying covariate and we simply break it down into two pieces. So we have the subject average here, and then we take the actual value xij and subtract that. So this is the subject average, and then this is the within subject piece. Because we're considering on a given day for a subject, how does that deviate from their overall average? And as you can see, we've added and subtracted that average for the subject. So we've maintained the equality here, but we've created two variables that are of interest. And so if we create our data set to have the subject average, and you'll just repeat that for each observation you have on a subject. And then you also have this new variable, that's the overall value for the subject on a given day, and subtract off the mean. And you have in your data set two new variables. And you just, in your regression, you include both of those. Then you'll have a coefficient then for this piece, which will reflect differences between subjects. And then one coefficient that will be in front of this one that will indicate changes within subjects. Okay, so to illustrate this, I have birth weight data. So this is a pretty common data set, and it comes from the CDC. So this is birth weight as the outcome for 880 mothers that had 5 children. So big families. The mothers were actually very young when they started having children. And so we're looking at, again, the outcome is birth weight. And the main predictor is the age of the mother at a given birth. Okay, so we have two possible models. If we just consider the age and we don't separate it out, that's the first model. Okay, so I'll have an intercept. We'll have a random intercept for each mother too. And then we have age of the mother, a slope for that, and then error. And then the second one, we break down into those two pieces. So we have the average age for mother I, and then we have the Xij minus the average age. So that's going to be, the deviation of the age based on when the particular birth was. And so in our model, we're just going to have those predictors. We'll have the average age, and then we'll have the deviation age. And so we'll naturally get two different coefficients fitted for that. Okay, so for the data that we have, if we fit model 1, we have beta hat is 17 grams, which indicates that increase in birth weight is about 17 grams per year. But the thing is, that's combining differences between mothers and changes within mothers as well, which that's okay, but you have to understand that there's two contributions. One that's based on between subject differences and one that's based on changes within subjects. So if we fit model 2, we actually get beta, the between subject beta is about 30 grams, and the within subject is about 12. Quite a bit different, right? And you can see based on that the 17 is essentially a weighted average of those two. It's got to be in the middle, right? Because we're pooling that information together. So how do we interpret those effects in this model 2, where we've separated out the between and within subject effects? So you can say we would estimate that average birth weight will differ by about 30 grams between two women whose average birth age differs by 1 year. And secondly, for a given woman, we would estimate that the birth weights of her children increase by an average of about 12 grams for each year that she ages. Now, part of this, why is there such a change within a woman? I think the big reason is because the cohort is young mothers. Okay, so they, very young, in fact. The median age at first birth was 17 years. Okay, so we're dealing with the cohort where the mothers are very young, and so if they're very young, they tend to have lower birth weight babies, but as they age, that increases. Okay, so this graph shows you predicted values from our model. And so the blue lines are individual mothers, and then the red line is the between mother average. I've thought about why are there differences? That's the next thing, right? Is to think about why are there such differences in these two effects? And I haven't really gotten a really good explanation for this. And so that's something we can wrestle with, is why is there such a difference between and within subject slopes here? But looking at this data, is there any other alternative way you might consider modeling these data? Any other ideas about if you were to actually build a model for this other than the one I showed you here? Any thoughts that come to mind quickly about how to model this?
You could do, because like 17 grams isn't necessarily a huge difference. You could stratify it as like low birth weight, no low birth weight, and kind of look at harder binary outcomes.
Okay, so looking at the outcome in a different way, that might be an idea. What would be a more flexible model than what we have here?
Introduce a random slope.
That's exactly what I was thinking. Why not add a random slope for time so that we allow each mother to have their own trajectory? That's what I was thinking, because this model is fairly constrained, just having a random intercept. What would be interesting, especially if you look at this graph, is to see, do some mothers, are they flatter, or, are some steeper? And really, there could be a point, there could be an age where it's not going to matter too much. Once you get to a certain age, maybe birth weights will kind of stabilize over time, right? So I think there's a lot of ways that you could get more flexible fits to better understand what's going on. And that's, like Randy said, that's the first thing that came to my mind. Another idea maybe is to look at the average function over time, and instead of just a linear function, to see if we may have some other function that is a little more complex, that may be quadratic or something like that, or cubic, or maybe even splines, if we have enough information to better understand that the age versus birth weight relationship.
Can I ask a question?
Yeah.
In this, it looks like all the women have at least multiple births, but like if you have a data set where you only have a handful of women with multiple births, but then a couple women with, or a handful with only one birth, can you still fit a model that requires one of the fixed effects to have like a time varying, like you would have to have a multiple measurement?
I think you could still do the same modeling regardless of how many you have, even if you have one in there. Yeah, and I had another thought I was going to mention. Okay, so this is one of the things, and this is a big issue, to be honest, is a lot of times people think they're going to make their data set cleaner by throwing out subjects. If subjects didn't complete the whole study, we'll just remove them. So that's kind of what we have here. We have a data set where we're specifically looking at mothers with 5 births, right? So we haven't included a bunch of mothers, and probably mothers that have 5. I mean, that's probably actually a small proportion, right? What's the problem? Well, a lot of times you introduce bias, especially if you're interested in inference for a larger population. If we wanted to get inference for mothers in general, you know, this study I think was done in Georgia. So like, if we wanted to do a study that reflected the population, we wouldn't be subsetting to specific number of births or anything like that. We would just get the data as we have it. And, you know, our model doesn't require that mothers have the same number of births. We could have a different number. And in fact, like Carrie's question, I think we could even include mothers that just have one, although they're not going to contribute really to the within subject part of the model. You can still include them in there, right? And it would contribute to the between subject effects. But that's a big issue. Like, and even now I'm dealing with clients who they, you know, intuitively they think we need complete cases. We need subjects that completed the study, their experiment, and we're just going to remove the subjects that were partial completers. And that's actually not the best way to do things if you're trying to make inference for the whole population. So we'll talk about that a little bit more next week as well. Any other questions or thoughts? This other data set, you know that I like running, you probably know that by now. And I've already presented some data on the Boulder. And so I use the same principles. I had multiple years for the Boulder, and I wanted to compare subject average function with within subject change functions. And so basically using the same principles, I did this with the Boulder data. So I'm going to zoom in a little bit so you can see it. On the left is the men, and on the right, oh wait, men and women. Yeah, so men is on the left, women's on the right. So you can see there's a dashed line that essentially is an average of everything we have. And that's going to be, you know, that's going to reflect, you know, we're combining everything. So I'll stop on what I was going to say and not say that until I walk through this a little bit more. But we have individual subjects are the gray lines. So for example, there's this runner, there were, I think 43 or 44 when they started running this race, and I had like maybe 8 years, consecutive years of data for the subject. And you can see this is my role model, because I would be about right here in age. And if you can run under 40 minutes and you're over 50, that's pretty good. So they're the fastest runner. Now, the runners that I included here were the top runners at each age. And part of the reason why I did that is because these runners are running very hard. They're very competitive. And so it makes it easier to make, to try to understand the aging effects, right? Because if we look in the middle, we're going to get runners that maybe some of them are running hard as they can, but other runners in the middle, there's going to be other factors at play. They may take it seriously one year and maybe not so seriously the next year. So the top runners, we know they're going to be pretty consistent from year to year in their effort. And that's why we chose the top runners. And so this, you see kind of the same pattern over time. There's sort of a quadratic pattern here to the data. I'm actually using a gamma type function here, and you'll notice that the decline on the left, it's much steeper on the left than it is on the right. And so with the quadratic, you just can't quite get that modeled as well as if you use this function here, this gamma type function. It's a nonlinear function, right? Because when we talk about linear functions, we're talking about, is it linear with respect to the parameters? And clearly it's not, because we have parameters in the exponents. So this is a nonlinear function, and you couldn't use mix to fit that. You'd have to use NL mix or something like that. But if you take the log of both sides, you can linearize that function with respect to the parameters. And so we have the log of race time is equal to alpha naught plus alpha 1 log of x plus alpha 2x. It works out really nice. And Gary Grunwald was the one that actually showed me this, like, and it's pretty obvious when you look at it. It's like, you know, why didn't I think of that? But I was fitting this one, the nonlinear function. Why is there a benefit to going to this one, the log here? What have we learned about, you know, linear mixed models compared to, you know, other types of, you know, generalized linear mixed models and so forth? Or maybe we need to keep talking about it. I'm not sure. Linear models are nice. You know, linear models are, you have nice, clear functions, and it's easy to add the error term. And there's just really nice properties to linear models. Things get complicated when you start considering nonlinear functions, nonlinear links, harder to interpret, not as flexible, more convergence issues. There's a whole host of reasons why if you can, you want to go with the linear model. And that's the whole reason why we use the pseudo likelihood approach, right? Even if we have that non-linear link, we develop a method to transform the data to be approximately normal so that we can employ proc mix. That's the whole reason why we do the pseudo likelihood, right? Even for an outcome that's not normal. Okay, we're trying to find a way to make things easier for ourselves. So the thing is, if we have xij, how can we separate that if we have this nonlinear function? Well, instead of adding and subtracting the mean for a subject, you can multiply by it and then divide by it. So it's kind of the same principle. I came up with this idea. I thought, wow, this is going to be a good paper, right? This will be a good publication. But the problem is, if once we log it, we're down to a linear function anyway. So it's kind of a nice point that we can do that. But for the data that we have, because we can take the log of the outcome and get it and linearize that predictor function, it's kind of a moot point, really. So here's a model we're going to fit the log of y, so the log of the race time. And we can, using the principle of separating between and within subject effects, we get parameters that have between subject interpretations and then some that have within subject interpretations. And I think I'll just get to the key here. From that, our between subject function is going to be, if we take, we set our random effects to 0 and we evaluate the function for xij at the average, we get a between subject function. And if we set the random effects to 0, but we don't evaluate xij at the average, then we have a within subject function. So we're separating out our function into two pieces, one that has between subject effects and one that has within subject effects. And I'm graphing here, the dashed line is the between subject function, and the solid thick lines are within subject functions considering different ages. So the average age for this subject was between 10 and 15, and then one between 15 and 20 and so forth. Now, do you see differences between the between subject function and the within subject functions here? I mean, they're fairly close, right? But especially after the peak age, you notice it's a little bit flatter for the within subject functions, a little bit flatter compared to the between subject. And especially for the women, you really notice it. What we can do is we can make interpretations. So with our longitudinal data, we're essentially separating out effects so that we can say, for example, a 42-year-old male will slow down by 1% compared to 41. Not slow down, but the difference is expected to be 1% slower for a 42-year-old compared to 41. And then the within subject change is looking at an individual subject. So a 41-year-old that participates the following year is expected to slow down by a rate of 0.3%. So that there's less of a change when you're looking at within subject, as opposed to comparing between two different subjects. Why is this? I do have one thought. It's that if you start running, let's say you start running when you're older. Like if you start running when you're 40 or 45, you have probably not as much to lose in terms of your race time because you just started. And so compared to the population average or the between subject differences that you see, I'm thinking that it makes sense that you would not lose as much, depending on when you start. If you start running older, then it takes you a while to get up to your peak form, right? It may take several years. And there's still an aging effect that's involved, but relative to the population average, you won't see as much loss, if you start running when you're older. And so to me, I think it's a little bit intuitive to see these differences between the between and within subject functions. Okay, but that's the harder thing. You can do this. You can separate out effects. We know the math how to do it, and then the question becomes, why are those effects different? So you can maybe, you can think about it, and you can, in your discussion in your paper, you can talk about those things, that the possible reasons why you might see that. Any other questions on that? That's 2 out of 3 things I wanted to talk about here. Some of this slide, modeling time as class or continuous, I'll just make a quick mention. What's the best approach? It definitely depends on the data that you have. So like for you guys in your projects that you're doing, should you model time as a class variable or continuous? Your data will probably dictate, which one to do. And if it's not clear, I would try both, and compare the two to each other. But certainly I would expect some of you to be modeling time, for your final model. Some of you may have time as class and some may have time as continuous. Give me 1 or 2 of the main reasons why you go one way or the other with it. This might be a little bit of a review, but just make sure we're on the same page here.
Well, if you have like 20 time measurements, that would be kind of wild to do as a class variable. So the number definitely plays a role.
Yes. So if you try to model time as a class variable and you have 20 time points, you're introducing a lot of parameters, and it's probably not going to be efficient. You'll probably be able to find some continuous function, even if it has a higher order polynomial to it, that's still going to use a lot less number of parameters, right? Yeah, that's a big one. Any other things that you can think of?
If people weren't measured at the same intervals.
Yeah, that's a big one. And you get that a lot with observational study data. They have, you know, different times of measurement. They may have different number of measurements. You know, some may have a couple, some may have 10 or 15. So that then it becomes really hard to use time as a class variable. You have to go to time as continuous. There may be some issues where you have to make a decision, even if you had planned it. Like this is a good example, COPD gene. We have data collection at what they call it phase 1. So this is baseline, right? The first visit. And then these subjects are supposed to come in 5 years later and get a second one. But the problem is they don't all come in exactly at 5 years, right? Some may come in at 4.5 or 5.5. So the question is, when you have that, does that mean that you have to model time as continuous? Not necessarily. You can still compare. And honestly, with that data, I still typically model it time as class because I've compared the two to each other, and I've seen that, you know, it's the close enough principle, you know, like how close does it have to be for you to model it, you know, as time as class? And it seems like it's still a reasonable approach using time as class in that case, but it's something you definitely have to evaluate with the data that you have and not just make an assumption that you can do it one way or the other. So unless you really do have exact measurements, you know, then you should probably look at the impact, you know, of follow-up that wasn't meeting when the design said it should be. So these are the slides I'm going to jump over. Inference when time is modeled as a continuous variable. We pretty much did this already. So these middle slides are kind of a review, and I'm going to jump over these. And I'm going to get to an important one here. Population average versus subject specific effects. So we're staying on the same theme, but we're going to talk about different models and effects that may have different interpretations based on these different models that may have different links or something like that. So beta parameters may have subject specific or population average interpretations depending on the type of model being fit. For normal outcomes, the interpretation is the same. Again, in normal land, in linear model land, the models are really nice. You can add things together. It's simpler. Effects have, you know, interpretations that are easy. That in this case, you know, we're going to show that the population average has the same interpretation as subject specific. So it works out really nicely. So in order to understand the difference between population average and subject specific effects, we're going to consider for our model, let's say we're just using a simple linear function here for time. Let's say x is time. And so the expected value of y is just beta naught plus beta 1x. Okay. And that's a marginal model, right? We're not conditioning on the random effects at all. So this is saying averaging over subjects, even if you do have random effects in the model, averaging over subjects, this is what you have. The subject-specific function we can consider by conditioning on the random effects. So in that case, you know, we have a given b here, and then we're going to keep those terms in the model on the right-hand side. Let's consider an average. What's an average subject in the population? Well, we can think of it as a subject that doesn't deviate from the mean. Okay, so that is b equals 0. Okay, so that's considering a specific subject, but they represent an average in the sense that they don't deviate. The random effects don't deviate from the overall mean. So that's expected value of y given the random effects are 0. For a normal model, what do you see? It's the same, right? So these effects, these beta effects have both population averaged and subject specific interpretations. Okay, so next you're probably thinking, well, when would they differ? So we're gonna look at a couple other outcomes. One's a Poisson and one's a binary to see if we're gonna get the same thing or not. Okay, so for the normal, the population average function is equivalent to the subject specific function for the average subject. So we say that the fixed effects in this case have both population average and subject specific interpretations. Next, we're going to consider the Poisson. And for the Poisson, we use the log link. So we can express the conditional mean. So this would be for the subject specific one. That turns out to be e to the beta naught plus beta 1x. Okay, so that's our subject specific, and then this one is going to be our population average. We're averaging over the random effects. And what's the difference here between those two? Well, the piece that has the actual predictor with the beta 1, those are actually the same. And the difference is only in the scalar amount, right? And because of that, the interpretations for the slope of the predictor is also going to have both subject specific and population average interpretations. Now, how do I get the expected value, to e to something that's normally distributed? How do you figure that out? You can use moment generating functions to do that. It's a theory thing that, you can do that for practice. So for the Poisson, we've shown for the predictors of interest, they're still the same interpretation. But what about a binary outcome? So in this case, we have the logit link, which is a little more complicated. And in this case, I've actually generated the data, I simulated it, because you can't really do it algebraically. So what I'm doing here is showing you the different functions. So the red one is expected value y, ij. And why is it a function? Well, it's a function of x, right? So you could actually say expected value of y given x. But like I told you before, that although that's true, we just assume it, because that's the case for all the regression modeling that we do. What are the dashed lines? These are expected value of y, ij, given b sub I. So this is for various bi values. So when bi is negative, you're going to get the functions over here. When bi is positive, you're going to get the functions over here. And then this one here, this is specifically the expected value of yij given bi is equal to 0 for that one right there. Okay. And then this is the red one. So what do you notice? You notice that the marginal mean, what do you notice about the slope? If you were to take the logit link, what's the slope of the red one compared to the slope of the other ones? It's flattened, right? The red one is flat compared to the slope of the other ones. And so the parameters that are associated with the expected value of y, those are different, right, than the parameters that would be in the ones where we've conditioned on the random effects. And so this gives you an example of where the effects in the marginal mean are different than the effects in the subject, the ones that condition on the subjects. So for binary outcomes, if you use a model and you don't add in the random effects, then those beta parameters are going to have population average interpretations. So that would be true for models like GE, right? Because we can't add in random effects. And so when you run GE, we get what we call population averaged effects that have population average interpretations, as opposed to models where we can add random effects like generalized linear mixed models. Those associated parameters will have subject-specific interpretations. Which one do you think is better? Well, there's not a better, they're just different, right? The thing to me is that, like, if this model actually represents real data, if this is a decent model, then the thing that you notice that is the black functions, every subject in there is represented. They're shifted, right? But the slope for each of them, is for every subject is steeper than the red one. So if you're trying to make an interpretation and you're trying to understand how a relationship between some predictor, this maybe X is time or it's exposure or something, how that relates to a binary outcome, no one in that population has this red function. The red function is obtained by averaging over subjects. So it's a completely different interpretation. And I think epidemiologists would tend to like this red function, but it has a different meaning than the subject-specific ones that are represented in black. So implications. So I wouldn't say that one is necessarily better than another, but to me, I understand the subject-specific one a little bit more readily, I think, than the population average. If I were an epidemiologist, maybe I'd have a different point of view on that. So again, if there's subject heterogeneity, for example, random intercept differences, then using GE will yield beta estimates that have population average interpretations. Using generalized linear mixed models, with the appropriate random effect terms, we'll have beta estimates that have subject-specific interpretations. We also learn in pseudo-likelihood, using that approach for generalized linear mixed models, we have the option of doing the expansion about just the fixed effects or the fixed effects plus the random effects. And so if we add in the random effects, then the interpretations will be subject-specific. And if we set those to 0, essentially eliminating the random effects from that Taylor series expansion, then they'll have population average effects. And there's a little more detail if you look back in those slides, it talks about that. All right, so as a summary, a predictor that varies over subjects and time can be split into 2 components and separate coefficients given in order to estimate between and within subject effects, and otherwise it's pooled. For complex models used with longitudinal data, random effects can be added to the prediction part of the model to get subject-specific predicted values. To understand disease progression, you may want to consider including a time-varying age in the model instead of just baseline age, if you want to estimate progression that's not due to aging. And then some more just summary of points from what we talked about today. If we have binary longitudinal data and there's subject heterogeneity, so between subject differences, and we're using logistic regression, if we use GEE, then the beta parameters for the predictors have population average interpretations. If we use generalized linear mixed models and we include the appropriate random terms, then the effects will have subject-specific interpretations. Now, here's one question. I want to see if you guys are not falling asleep here. If we were to have more between subject differences for the data associated with this graph, more differences between subjects, first of all, what's going to happen to these dashed curves? Randy, yeah, and Chloe, spread them out. That's right. Go like this. They'd spread out. So what would happen to the difference between expected value of y and the expected value of y given b equals 0? What would happen between the difference of those?
It would get bigger.
It would get bigger, right? Because as you spread out those curves, the red one is going to get more and more flat, right? It's going to flatten out. And so there would be a bigger difference between the marginal mean and the conditional mean, given the random effects are 0. Good. So that's that. We have a few minutes. What I want to do, and I'm not going to get too far, but this is about what I thought. I thought I would get through these slides because of the fact that I jumped over the custom tests, which we've already done. I don't want to do that again. If you want to practice that more, you can, and if you want to talk to me more about it, we can. But this is going to be a little bit of a teaser on missing data, and we're going to talk about it more next Wednesday. So, like I said at the beginning, missing data is a big issue for longitudinal modeling because dropouts occur, and the longer your study goes, the bigger of an issue that it is. But just to sort of whet your appetite here, let's say that we have 2 visits and we have 7 subjects, or 8, I should say 8 subjects. And here, I'm not showing you which subject, how they're related between the visits. So it's not a scatter plot. It's not a line graph. It is a scatter plot. So we have everybody at visit 1, and then we have 3 people that drop out. Now, if you don't know how subjects are connected, which subject, how we should connect these lines based on the repeated measures, then what's your best guess at the average progression? If you don't know any better, you would just take the average of the points at visit 1, right? And the average at visit 2 and say, okay, let's just connect those. Connect the 2 averages. We're ignoring the repeated measures, right? That's as best as you can do with the data. But if we knew subject 1, 2, 3, 4 are here, now we're seeing something that the researcher didn't see. They didn't see these lower 3 subjects. For some reason, those 3 values at visit 2, those subjects dropped out. So we're looking down on this. We have a perspective like God's. I guess you can say that we can see everything. The researcher did not see 3 particular responses at visit 2, but we can see that, right? So what happens if you're to take this data and use a mixed model, and let's say the slopes tend to be pretty consistent, so let's add a random intercept for subject. How will this be modeled with the mixed model? Is it just going to use the average of visit 1 and the average of visit 2 to get that average progression? No, this is actually what you'll get if you use a mixed model and you have a random intercept, even if you just include the visit 1 for those 3 subjects that dropped out at visit 2. Our predicted values are going to make sense. Okay, so by addressing correlation in the data helps us to get smart values. I call them smart values. And it happened to work out. Now, we didn't know what those would be. It happened to work out for this data set, but mixed models will smartly estimate predicted values for both subjects and the overall average based on the model that we have. So it's not just going to pool everything at visit 1 and pool everything at visit 2 and get something that's going up. It's going to essentially look at the relationship that we have between the 2 visits for the subjects and say, this is what we saw for the ones that we did observe. Therefore, that's what we'd predict for the other 3 subjects. Now, if we had a situation that looked like this, then it's going to be hard to estimate it, right? Because we don't see these increases. We don't have that information. So if we did that same approach here, we'd be estimating that these would go down, right? Because the researcher did not observe that. So this would be a situation where the missingness is informative, and honestly, there's no good way to do it unless we were able to make some assumptions, smart assumptions, or find more data that informed us about why those 3 lower subjects would be going up. Okay, and then lastly, what about this? We have a situation here where the change is directly related to the starting value. And so if we're able to understand that we see a pattern where as we decrease the intercept, we're starting to decrease the slope as well. And if we were to make that assumption, then we could actually estimate these appropriately if that assumption was correct, if there's a linear relationship between the change and the starting value. So missing data methods are hard because you really don't have a way to check your assumptions like we do with a lot of other model assumptions that we have. The best you can do is try different approaches, or maybe go in and resample. If you can go in and resample subjects, then you have a way of checking your assumptions. But next Wednesday, we're going to talk more about different methods you can apply for missing data. All right, so that's the teaser. So Monday we have a quiz, and it's going to be the same approach that we did for the first quiz. It's just that now we're going to, the material is going to be over advanced mixed models, and then maybe one question on like generalized linear mixed models and stuff like that. I do have office hours, so if anybody wants to, does anybody plan to hang around for office hours? Let me stop my recording.